Welcome to Roman numeral 6 on kinematic equations. Remember, when we talked about kinematics, that was the study of motion without considering the cause. So now we're going to take equations and some of the concepts we've learned so far and apply them to motion for objects undergoing a constant acceleration. I put this chart in your notes because it's really important that you understand the units. When we get to the word problems, sometimes you may not be given a specific name of a quantity, such as the distance is or the displacement is so many meters. It'll just say, for example, an object moves 10 meters. It's up to you to know that that would be a distance or a displacement. So that's why I put this in here. One of the easiest ways for you to recognize which numbers are going to be plugged in for which variables will be right here using the units. Okay, and remember, no naked numbers. Every number needs a unit with it. So keep this chart in mind as we continue to go through this section of the notes. There are 3 kinematic equations, and out of all of the variables that can possibly be used, you'll see a distance or displacement, an initial speed or velocity, a final speed or velocity, an acceleration, or a time. All of the equations have 4 out of the 5 variables. So you'll notice next to each equation I put no with a blank, so we're going to see which variable is missing. For example, this first equation, there is no d. So we're going to have the final speed equals the initial speed plus acceleration times time. So if you see a word problem and it mentions meters or some sort of distance or displacement, that's a pretty good indicator that you will not be using this formula because it does not have anything with meters in it. Another thing to note on these equations is that they will be the same for scalar and vector quantities. So if I were to use initial and final velocities instead of speeds, I could add the vector notation to each quantity that is a vector in my formula. And time's always a scalar, so that one does not get the vector notation. So again, you can use any of these formulas as scalar or vector quantities. Let's move on to our second equation. This one, you should notice that there is no final speed or final velocity in that particular equation. And then lastly, time is the quantity that's missing. It will be helpful for you to memorize these equations or at least keep them handy while you are doing your quest problems that we go over together in class. Now, some of you might be really good at doing word problems, but in case that's something that gives you a little bit of trouble, I wrote down a technique that I've seen be really successful with other students. So it is called the guess method. For every problem, we are going to write down the givens, U will write down the unknown quantity that's being asked for in the problem, E decide which equation is going to use those givens and unknown, then we're going to solve the equation for the unknown variable and substitute in the numbers for the equation and solve to get our final answer. So let's practice. The first example problem has a car with a velocity of positive 24 meters per second accelerated uniformly at a rate of positive 1.9 meters per second squared for 6.5 seconds. We are asked to find the final velocity. So what I did was I wrote down every number that's given, and now we're going to go back and assign a variable to each of those numbers. Remember that chart on the very first slide in this video? Well, we can use the units to help us identify which variables are going to go with which numbers. So I'm hoping you recognize that meters per second is a type of velocity. In this case, it's going to be the final velocity, and since those plus and minus numbers were given, we are using the vector versions of all of our quantities. Acceleration is the meters per second squared, and time would be measured in seconds, and then lastly we were asked to find the final velocity. So now what you would want to do is go down the list and see which of the 3 kinematic equations match up to our givens and our unknown. I hope that you recognize there was no meters in this particular question, so that's going to leave us with the first formula. Luckily, we don't have to rearrange anything. Final velocity is already isolated on the left-hand side, so now we can just plug in our numbers and solve. So take a moment to do that and then come back and check your answer. Notice that the units work out to meters per second, and we got a positive 36.35 meters per second for our final velocity. And remember, if you're using the correct number of significant digits, you would simply just say the final velocity is positive 36 meters per second. Let's try one more. Determine the displacement, so that's going to be our unknown, and displacement is a vector quantity, of a plane that's accelerated from one value of meters per second to another value of meters per second. Those are both velocities, so we're going to assign them as initial and final velocities, and then time is the easy one to recognize, and that's 13 seconds. Did you notice what all of the kinematic equations had in common? Well, they all had an initial velocity, and they all have an acceleration. Do you have an acceleration here? No. So that means we're going to have to find that first. So remember, physics builds and builds on previous material. So let's get our equation for acceleration, plug the numbers in, and find that value before we get to our kinematics equation. If you tried this on your own, you should have gotten a value of positive 1.69 meters per second squared. Since this is a number we're going to need to plug into another equation, you don't want to round too early, so do not round this up to positive 2, otherwise your final answer is going to be slightly incorrect. Now that we have the acceleration, we just need a formula that has displacement in it. So I'm going to use the second kinematic equation. Now let's plug our numbers in. So if you paused the video and tried this on your own, you should have gotten about 1,078.8 meters. I also changed that to correct significant digits, so we're going to use scientific notation, and that would be a positive 1.1 times 10 to the third meters. If you did not get one of these answers, I would go back and check and make sure that you squared the time in that second part of the equation, so that's actually 13 squared when you go to multiply. And also make sure that you didn't forget to multiply by the 1/2 in this part as well. If you didn't get these answers and you're still not sure where you made a mistake, then come in and ask me and we can go over those together. You try the last problem, pause the video, and come back and check your answer. You should have gotten somewhere in the neighborhood of 37 meters per second. Don't forget to square root at the end because that was VF squared and we want just the final velocity. Next, we're going to talk about acceleration due to gravity. You should know by now that if you were to let something go and drop an object, gravity is the force that makes it fall downward. Well, it starts out at rest, and then it actually does speed up as it's falling, and we call that acceleration due to gravity. Because the object is speeding up, it is accelerating, and gravity is the force that's making it do that. So, whenever an object is in free fall, which means there are no other forces acting on it besides gravity. You just drop an object and let it go, and gravity is the only thing that pulls it down. So that's called an object in free fall. And any object that's near the Earth's surface has a downward acceleration of 9.8 meters per second squared. You'll see that written as an A for acceleration, or because it's a special one that's always true near the surface of the Earth, we also can term it as a lowercase g. It's up to you, whichever one you prefer. I'm probably going to use the lowercase g just to let us know that that acceleration is due to gravity. This is a number you will need to memorize, so I did put a little asterisk here for you. You're going to use this value as the acceleration anytime an object is dropped. So that's a key word that you'll look for in our example problems. And then number 2, an object in free fall has the same downward acceleration whether it starts from rest or if it has an initial velocity in the same direction. So gravity treats every object the same whether you throw it down or if you just let it go and have it fall on its own. In our class, we are going to neglect air resistance. So this is something that's really important. That means that we're going to have a happy little physics world. Air resistance doesn't exist. Every object is treated the same. Our kinematic equations look the same. All we're doing is substituting the A with a G. So go ahead and take a moment and write down the new value, or the new look rather, for the kinematic equations in your boxes. Remember, everything's the same, you're just replacing the A's with G's to indicate that the acceleration is due to gravity. So I'm going to do one example problem with you, and then you'll do the last example on your own and see how you do. So this one, we've got a student dropping a rock from a bridge. The water is 15 meters below the bridge, so that should tell us meters is going to be a distance. With what speed does it strike the water? Well, that's going to be the final speed as it's landing. And you might think, wow, there's only one piece of information. However, you do have other numbers that you would be expected to supply. So I went ahead and gave you a hint in this example problem. If something is dropped, remember that it will be accelerating because of gravity. So we know that the value for our acceleration is a 9.8 meters per second squared. And also, the object was dropped, it was not thrown down. So because it's dropped, that also tells us that the initial speed is going to be 0. So we've got these extra two numbers right here, simply based on an object being dropped. So remember, there might be times when you're expected to supply extra information that's not necessarily stated in the problem. So you want to use those context clues and infer that extra information. So look back at your kinematic equations, the ones that we rewrote for gravity. You should notice that time is missing, so we are going to choose the equation that does not have time in it. Hopefully you recognize that that would be the third equation. So now let's plug in our numbers. At this point, when you multiply out all of the values that were given, we should have a final speed squared of 294. And then our units gave us meters squared per second squared when we multiplied these two together. Our last step, we want to take the square root of both sides, and that's going to give us a final answer of approximately 17 meters per second. And we were asked to find the final speed, so you don't have to worry about a direction. There's no plus or minus sign, it's just 17 meters per second. This last example problem is a two-parter, so I'm going to set you up and let you write down everything that's given, and then I'd like for you to pause the video, try the question on your own, and then come back and check your answer with my solutions. These are the values that we can take away from the problem. A time of 2.8 seconds. We know that the object was dropped, so that lets us know that we have an initial speed of 0 and that the acceleration is due to gravity, and that value is 9.8 meters per second squared. The first part, we are asked to find the final velocity in meters per second. So pause the video, try this on your own, come back and check your solutions. I hope you were able to figure out that we use the first kinematic equation, then you're going to substitute your numbers and get a value of 27.44 meters per second as the final velocity. Remember, velocity is a vector quantity, and there were no plus or minus signs to indicate a direction, but we can logically figure out that the velocity is in the downward direction because it is falling, so make sure you include a direction as part of your answer. Now go ahead and pause and try the second part of the question. One equation you could have used would be the second kinematic equation. When you plug your numbers in and solve, you should get approximately 38 meters for the height of the bridge. I wanted to point out that you could also solve this particular part of the problem in another way since we do have enough information. So I'm going to show you that as well. Because we found that final speed in part A, or that final velocity rather, we could use the third kinematic equation and go ahead and solve for D, so we can go ahead and rearrange that. You should recognize some of these equations from the algebra review, so now we're putting those equations into practice and rearranging them. In this case, we solve for D, and when you plug the numbers in, notice that you do get the same answer of 38.4 meters with either equation. So when you're taking your test, if you notice something like this and you have the extra time, go ahead and try both equations and see if your answers are pretty close together. It's a really good indicator that you've done the problem correctly. It's just an extra way to check your work. So in class, we're going to be using your Quest assignment to practice with some of these problems, and I also have some other worksheets for you so that you can get really good at these before our next test.